binary record. All right. Okay. I hope you still remember the you know, this formula of how we convert digital value to analog value to digital value. All right. Okay. This is very basic and very important. You will be asked about this thing in the test, so you better get yourself, you better know this thing. All right. Again, let me recap before we continue further. All right. This is the analog values. All right. In terms of voltage. All right. Then this is more or less the decimal representation. And this is how basically the digital output representation, depending on the number of bits. In this case, we are working with 8 bits. All right, we have from here we can basically know this is 8-bit system. Okay, this 8-bit basically represent our ADC resolution, all right, as you may have seen previously. And when we have some other analog input values, in this case we have 1.2 volts, all right, and the system is currently running on the power supply of 5 volt. Okay, and then how do we convert this voltage value into digital value? All right, again, you have to remember when we work with 8-bit system. Okay, we have to know that to get the maximum number of level, in this case, we have to use the formula of 2 to the power of n. Okay, in this case, n is equal to 8, and I think you will get 2 to the power of 8. Can somebody calculate that for me? Someone? Anyone?
256.
256. All right. You have here 256 level. Okay. But this level now, if you can see from here, is from this 256 includes 0. All right. So that's why in total you have from 0 to 255. Okay. 2 is included in this 256, right? If you take 2, okay, the power of 8, you will get in total 256, right? The number of levels. If you include 0, you will get from 0 to 255. That's why you are looking at this full scale value of 255. All right, I hope that very much clear. This is the analog input value. Okay, so you divide by 5 because 5 is your operating power supply, and when you want to convert to digital, you have to multiply by the full scale value of that digital representation. In this case, if you are working with 8-bit, our maximum value is 255. Okay. Which the exact amount of level is 256, but if you want to put into calculation, you have to go to the maximum value, decimal. Okay, this is decimal value of 0 to 255. Okay, again, the number of level is 256. If you want to convert the value, you need to use the maximum decimal value, which is 255. Okay, that's why in this case they are using 255 for conversion. And of course, when we run the formula, we are getting 61.2. Of course, 0.2 will be decimated to this one, and you get only 61. All right. So 61 you have to convert to analog form, digital form. All right. For this particular purpose, basically, you can use your scientific calculators to do the transformation, basically. All right. So the same goes with these 3.7 volts. All right, we use the same formula and method. You will get this, and of course it goes to 189, and you can use your scientific calculators. You can convert from 189 decimal to digital 8-bit representation. All right. then you will basically get this representation in digital world, which represent again, um, number, this one, 3.7 volts. In digital world is 1011111101. All right. So this is basically how the conversion happened. Okay. There are some exercise here. Say if we consider a thermocouple giving the output of 0.5 milliwatt per degree Celsius, what will be the watt length required when its output passes through ADC if the temperature from 0 to 200 degrees Celsius are to be measured with a resolution of 0.5? Guys, please take 5 minutes. You can try it on your own. Try to solve this thing. I have solution in the next slide, but just take some time to try to go through this question. All right. Take 5 minutes, guys. Try to work on your own on this exercise. We'll see the solution after this. Cuba dulu Dah dapat ke? Boleh kira. Okay, the question says, consider a thermocouple giving output of 0.5 millivolt per degree Celsius. What will be the word length required when its output passes through an ADC if temperature from 0 to 200 are to be measured with the resolution of 0.5 degrees Celsius. Alright. Ada yang dah kira ke? Semua tak kira, tunggu jawapan. Anyone? Okay, we have first information is the transfer function of the sensor. Okay, and we will ask to find the information of word length. Here, word length would refer to the number of bits to represent the whole system. Okay, they say the temperature from 0 to 200 degrees Celsius. All right, then and if we have 200 degrees Celsius, more or less we know what they call it, the maximum voltage that we could get from the sensor, right? Just scroll to the answer. The full scale output from the sensor is 1, okay, 200 degrees Celsius times 0.5 is the sensor transfer function. Okay, then you get the full scale output from the sensor is 100 millivolts. All right, this is all you're gonna get from the sensor. Okay, even though now the temperature is at 200 degrees Celsius, you will basically receive maximum 4.01 volt, all right, from the sensor. Okay, the word length here is that the voltage divided by this one, 100 millivolts. Okay, all right, this one would be more or less 1 over to the power of n multiplied by 100 millivolt here, something like that. Then for a resolution of 0.5, we must be able to detect the signal change, in this case 0.5. Okay, the information here is resolution of 0.5 degrees Celsius. So we have to convert 0.5 degrees Celsius to voltage. We will have 0.25 millivolt. This is the minimum change. All right, the minimum change would refer to the resolution. All right, the minimum change that the system must be able to detect. All right, we have information in terms of 0.05 Celsius. We have to convert this unit to voltage. Okay, and here we get 0.25 millivolt, meaning that the system must be able to detect the minimum change of 0.25 millivolts. All right, so in this case, if you use 0.25 millivolt, all right, then as the smallest step, okay, then you will have to find the number of n in this case. All right, so you will have basically from this formula, you will basically get the answer. N will be 8.6. Of course, you go for something bigger than this, so we can basically decide to the 9 here. Okay. You all faham tak? Did you get this, guys, or you have question? So this is the smallest unit that we have to detect out of 100 millivolts. All right. Of course, you can always use this formula to detect the number of bits required, basically. So you can, if you can use this formula here, is equal to 0.25 millivolt V here, so you can find the N right here. Okay, so find the N. Basically, you will basically this N in this formula, you will get this kind of value, and then of course you know what to do. Is this clear, guys, or you need further explanation? No?
Yes, clear, doctor.
It's quite clear, right? So again, we have seen the some conversion from decimal to binary. Okay? In a typical numbering system, they have hexadecimal in place. So basically, you have to know how this conversion system works, how the representation from decimal going to hexadecimal and going to the binary. Of course, hexadecimal thing, you have number until 9, then you will start from A, B, C, D, E, F, which represent 15 in decimal and 1111 in binary, right? This is 4 digits digital conversion to hexadecimal, and then from hexadecimal to decimal, right? This is some kind of table which you can find basically anywhere. You can always refer to. All right, so this is basically how the conversion works. All right, I'm not going into the detail of this thing, because you basically have to how to convert from this is binary going to the decimal. Okay, basically you just have to do some, you have to select digits with 1 here, then you have to see the number, the location and the position of the bits. All right, for example, here we have 2, because this one 2 to the power of 0 and 1, in this case 0 0 1 2 3 4, so you have to plus power of 4, then 4 5 6 plus 2 to the power of 6. All right, and then you go 7 8 8 and 9, so plus 2 to the power of 8 plus 2 to the power of 9, and so on. We will get the total sum up to this number. All right, this is basically how the conversion works from binary to decimal. Okay, kat sini tak ada apa. This is nothing. I'm not going through this. All right, this is of course another version of the EQ system. Okay. Okay, in this case, you have basically more than one sensors. All right, all of these things are basically your signal conditioner and all that. All right, sensor, signal conditioner, and because you have more than one, you have to use multiplexer. Again, we have seen multiplexers operation in the previous class. If you don't understand the multiplexing job, you can always ask question. All right, stop me and ask. All right. I'm not going through the detail of this thing. This is just another diagram of typical the ecosystem. All right. Of course, as a basic unit of system of instrumentation, we always work with only one sensor. But in the real world, data acquisition receive input from more than one sensors. All right. They have until 1,000 sensors. All right. And of course, to be able to do that, you have to work very well with the multiplexer. Okay, this is another example. Okay, you have sensor. This is our Wheatstone bridge, if you still remember. Okay, this is the sensor. Okay, then you have amplifier, you may have filter, and then of course this is basically ADC punya job, which you convert from analog to digital. So I think more or less you know what this diagram is talking about. Do you have questions so far, guys? No? Any question?
No.
No question. Are you guys listening or you guys leaving?
But doctor, are you recording this lecture?
Listening up.
Thank you for responding, guys. This is like
Doctor,
yes.
is the lecture being recorded?
Yes. Thank you for the
Okay,
nice
thank
question. All right, thank you, Abdullahi. What they call that? Yes, it is recorded. Okay, so this slide you are looking at multiplexer again. All right, we have discussed about multiplexer previously. Of course, you know multiplexer's job is to do multiplexing, which basically selects one input at a time. Okay, so multiplexer would basically works as a switch, which they go round and round all the time and change the input. All right, and then multiplexer depends. In this case, this is analog multiplexer. If the multiplexer basically position before the ADC, this is analog. All right, you can also move this multiplexer into this position as a digital marks. Okay, of course here you have many sensors that you have to connect to lah. All right, so this is your sensor. Okay, so of course you can position multiplexer on the analog side or in the digital side, depending on your arrangement of instrumentation system. Okay. Yeah. 3-bit addresses for selection.
Doctor,
Yes.
which is better for the multiplexer, in the analog side or the digital side?
All right. Thank you very much for the question. The problem with analog system is that is noise, basically. All right. If you look at any multiplexer system, analog multiplexer, you will have some kind of switch. All right, which basically happens solid state kind of switch, which choose this input and then analogically choose the next one and the next one, the next one. Basically, during the switching of these inputs, the multiplexer itself can introduce noise into your signal. All right. If your incoming signal is basically, for example, 5 millivolt, okay. When they go to this after multiplexer, it can get 5.7 millivolts. All right. This is the problem with any, I would say, analog system. All right, the noise is a big issue. It's a big disturbance which you have to handle. All right, if your system is running, I would say, on a high voltage and you don't care about this small millivolts, nanovolt noise, maybe you don't mind putting multiplexer on the analog side. But if you are working, for example, in the stage of nanovolt, all right, and the multiplexer, when they do switching, they can introduce noise at millivolt, then your signal will be very gone and I would say interfered and interrupted by the multiplexer itself. All right. For example, you are expecting something at nanovolt to be displayed at your computer. All right, because you want to detect something on nanovolt, but your multiplexer is so noisy. They introduce some noise in millivolt, so your information in nanovolt will be buried and will be basically lost. All right. If you work with digital marks, basically, all right. If you work with digital marks, which will put the marks on this side, okay. After ADC, all you receive is 01, 01, 01, okay. So in this case, you won't be having any trouble with noise and all that, because your information is either 0 or 1. All right. Okay. And here you are looking at switching in this direction. All right. In which multiplexer would normally come with the frequency and switching speed. All right. Okay, maybe it takes sorry. Maybe it takes 100 milliseconds to do switching. All right. Some multiplexer takes 1 nanoseconds to do switching. So you have to select the fastest one. Of course, the fastest switching would go for the higher frequency. Okay, and this one, the slower switching would be good for low frequency application. All right. Whereas for digital marks, you are looking at the bit rate as the measurement of rate of conversion, meaning that these marks can switch how many bits per second, for example. So you have to know your bit rate before you can select the marks. All right. As for the case of analog multiplexer, you have to know your frequency of information before you can select the multiplexer. All right. The multiplexer should be able to, I would say, to do the switching fast enough before your, I would say, before the information comes again. All right. For example, for this multiplexer thing, I would go for example, if I have a kind of sinusoid here, okay, which my sampling frequency is 50 Hertz, all right, and my T would be 1/50. Can somebody get this thing for me? Berapa second? 1/50 Hertz?
0.02.
0.02.
02.
All right. So my minimum sampling time. Sorry. I got it wrong. This is our signal frequency. Okay. This is our signal frequency. The sampling frequency is basically double, so it's 100 Hertz. Okay. So you have to do this. Can you guys get this thing to me again, berapa? 0.01. Betul?
Yes.
So you have to make sure that, okay, the information is coming at 0.01 second. All right. This is 10 millisecond, betul? So maknanya every 10 millisecond, okay, this is your sample. Okay, this is the next sample. This is the next sample. I'll put it on the discrete punya pass train. Okay, this is T. This is 10 millisecond. This is 20. This is 30. All right. This one should be representing the waveform yang dekat atas ni lah. Alright. So your system should be able to capture the analog wave at every 10 milliseconds. This is minimum. If you capture more, if your system is slower, which you capture more, you won't be able to get this sinusoid in the digital world. All right. I hope you can follow me on this. All right. So minimum 10 milliseconds. If you do this sampling faster, for example, 5 milliseconds is always better. But your minimum, your maximum waiting time is 10 milliseconds. All right. So if you want to go for example, I'm working with a multiplexer, okay, which receive 3 inputs. All right. So each of these input basically is a sinusoid. Okay. So I have one signal coming in. Okay. Now my mux is basically switching to this one. Okay. So the switching time what they call that, specified by the mux must be less than 10 milliseconds. Okay. Less than 10 milliseconds. This is 10 milliseconds. Okay. Within 10 milliseconds, the mux should be able to go through everything. If you have these 3 input, this 10 milliseconds, sorry kat sini ada, okay. Okay. Switching time, you have to get 10 milliseconds divided by the number of channel. Okay. In this case, 10 milliseconds over 3 channel, you will have berapa? 3 point. Okay. So the switching time for the mux must be at least 3.33 milliseconds, because from this guy to this guy is 3 milliseconds. This guy is 3 milliseconds. Of course, you want to go again. All right. So 3 milliseconds switching. So that when you have the total of 3.33, you have 10 milliseconds. So that when multiplexers spend time switching from one input to another, they have enough time to come back before the 10 millisecond ends. All right. So this is what I mean by the multiplexer switching time property. When you design any kind of signal data acquisition system, you have to aware of this thing, and of course put into your design consideration. Do you guys get this point? No?
Yes, thank you, Doctor.
All right, meaning that from first switching time and switching to all of the input until it goes back, it has to be less than the sampling, this one has to be less than this, because when you finish, you need to look at the next input, which is 10 millisecond, 10 millisecond, 10 millisecond. Also the same for this guy too, all right? So, 10 millisecond and all right? Because after the mux, basically, after the mux switch to the first one, okay, they will pass through this one. When the mux switch to another one, they will read this one. When the mux switch to the third one, they will read this one, and they will start over again to go for the next one. And basically this is the process, and you know how the timing consideration should be. All right. Any question, guys? No. Okay, this is sample and hold. Sample and hold. It says here, taking the snapshot of the sensor signal and hold the value. Switch, connect the capacitor, and capacitor hold. This is how the the circuit and the system works. Basically, we don't have to pay much attention to this because sample and hold circuit will be embedded in ADC chips. All right, you don't have to basically do all sampling, sample and hold. Then you don't have to worry about it because again, this whole system and circuits are embedded into the chips. All right. Once you select the ADC or multiplexer chips, basically this thing will be specified for you. Okay. The software, you know, you can basically, you know, there are tons of DEQ software available on the internet, mostly tuned and designed to a specific hardware. Okay, of course, the most popular one is basically the LabVIEW. Of course, in this lecture, I'm not going to go into the detail because LabVIEW itself is a big thing which you have to work with the hardware system. All right. So basically, the lecture is more or less finished. I'm going to go for the next stage. We are going to work on some design thing. All right. Do you have any questions so far? No?
It's okay, Doctor.
All right, thank you. So in the next section, I'm going to look at into some design of system of instrumentation. I have some requirement, and I'm gonna ask you to think together with me to solve this issue. All right. In this case, I have some problem. Okay. Okay, I want to read what they call that. For example, in our house appliances, basically, I want to know the amount of current that are being used by my, for example, TV. All right. So I want to know how much is the current consumption from my television, and I want to design a system of instrumentation which basically can read and tell me that. All right. For example, my TV system is running at maximum 10 M. Okay, and I want the reading to be as good as 0.1 M precision. Okay. Okay. So this is basically my requirement. All right. So I want you guys to think with me. You want to design a system of instrumentation to read this. All right. Of course, the voltage is 240 volts. Okay. And I want just to read the, of course, for any AC system, the voltage is very much fixed. Okay. The only thing that changed is the current. So I want to build a system which can read the number of the current that flows through my TV. All right. Did you guys get my point here? We have some problem, and we want to solve the problem by building and designing a system of instrumentation. Boleh yang clear?
Yes.
So of course we always go back to our basic block, which is the sensor. Okay, then we have our signal conditioning. Then we have our ADC. Then we have our display. Okay, so this is very basic thing which you need to put in your mind, because in the next coming test and final, I will be asking a lot about this basic thing. All right, in everything that you do, you must be able to always get back to this thing. All right, so now we are basically measuring measuring current, so we need to find the sensor. Let's do it together basically. Let's try to find the sensor, right? I hope you can see what I'm doing. Boleh dapat
Yes.
Boleh You guys are seeing this?
Yes, doctor.
Alright, so now I want to design something. I'm looking for the sensor. Kat sini nampak macam menarik. Alright, let's look at this. Wow, they can go up to 200. Okay, I only need something at 10 amps. So kat sini sampai 200. This is a lot. So I'll be keep on looking for something close to 10 amp. Alright, this is 50 amp right there. This is 50 amp. Or this is 300 amp. Ada tak yang kecil-kecil punya? This is 100 amp. 50 amp. The information. The current sensor. I'll go for this one. Let's go to Shopee. Okay, alright. How do I work this thing out here? Okay. So I have this is 100 amp. Okay lah, I'll just take it. Okay. Tak apa, kita Google lagi tengok. Okay, I want to find something. Current sensor input range. Let's look at this. Okay. I just take a random problem, and let's see if we can work this thing out. All right. Now I'm looking at the current sensor. Okay. We have a good input range here at 0.01. Okay. The output is 0 to 5 volts. This is analog output. Okay, and then of course the power supply can go to that point. All right, input range is okay, response time is okay, frequency 500 Hz, offset voltage, power consumption, isolation, hysteresis error. Okay, I think I just need some data sheet. Now we are looking at data sheet. Okay, meaning that the full scale accuracy 1%, linearity 1%, so that's all right. Okay, now we have a sensor, 5 volt, 0 to 5 volt, all right, which will give us maximum 0 to 10 amp. Betul tak? Tadi kita tengok dekat datasheet. Betul So we have accuracy 0.01, okay, which is good enough. Okay, they have output 0 to 5 volt, 4 to 20 milliamps. This is a standard current output. You can choose 0 to 10 volt. You can choose 0 to 4 volt. In this case, I would basically take 0 to 5 volt. All right. And of course, we have several options of power supply. It's okay. I think I will just go for that basic power supply system. Okay, this is the output. Okay. All right. So we have maximum of 5 volts coming out here. Okay, And what we do next, we are done on selecting the sensors. Okay. What shall we do next? Anybody? We want to make sure that we can display, for example, 5.7 amps. All right. I want to get this kind of reading at the end of the display. All right. What should we do? What should we do next? Anyone?
We select the condition, the signal conditioner.
All right, now you should go to find the signal conditioner in this case, because we have sensor running output maximum 5 volts, so you should basically consider the whole thing running at 5 volts. All right. So I'm putting some assumption here that the signal conditioning is running 5 volt. I'm putting also ADC to run at 5 volt. Of course, my display system is also running at 5 volts. All right. So, for example, I need precision of 0.1 as a basic unit. If I take 0.1 volt, 0.1, sorry, we have to do some kind of here. Okay. So you have to do some kind of conversion here to see how many amps that we get. All right. To get 0.1 or 0.1 amp. Okay. What is the value here? Can anyone give me? 0.1 amp is something that I want to observe on the accuracy at the end. 10 amps is basically the full scale reading of the sensor, and 5 volt is basically the maximum voltage that the system can give. All right. What is the value here? Can anyone calculate for me?
0.05.
0.05
0.05.
0.05 volt. Okay. Per 0.1 amp. Okay, so meaning that the whole system must be able to read the minimum change of 0.05 volt. All right. So this is the system precision that we basically need. Okay. So what kind of signal conditioning do I choose? All right. In this case, I get a voltage output. Okay. I get voltage output after the signal after the sensors. So what kind of signal conditioner do I need to choose here? Okay, because everything now is running at 5 volts. Okay. And of course, this maximum things here, I have 5 volts. What do I need to choose here for the signal conditioner? Anyone? Anyone? Because everything now is running at 5 volt. Okay. Here also 5 volt. This is also 5 volt. All right. And the maximum information I have here is 5 volt. So in this particular case, guys, I don't have to do anything on this signal conditioner. Okay. Meaning that I have to just find any kind of unity gain amplifier. Okay. So if I give 5 volt, I will basically need 5 volt to go out. Correct? Am I right? Do you understand this thing correctly?
Yes.
Unless if I change the voltage here to 10 volt, what should I be doing next? What should I be doing next? Again, come again. All right. In this case, because the ADC is running at 10 volts, all right, you may want to consider to get some kind of you know, amplifier. Gain equal to berapa?
2.
2. All right. Okay. Did you guys get this? Okay, because it is very important for any system of instrumentation design, you have to watch out you have to always watch out the operating voltage of all of these components. Okay, because whatever information that you are sending, you have to make sure that everything comes in to work at the maximum operating voltage of that particular units. All right. My information from sensor is 5 volt. All right. And my signal conditioner is 5 volt, so I don't have to do any kind of conversion. All right. Okay. And then I'm sending my information to ADC. The ADC, when ADC basically has 5 volt operating voltage, all right, my full scale ADC from I would say from 0, 0, 0 to maximum of 111 would be to the 10 volts, all right, in this case, all right. The information that you basically receive from signal conditioner is just 5 volt, okay. Maximum scale. When this thing goes to ADC, your information will be truncated at this level, and you will use only half of the ADC bandwidth. That's a problem, okay. That's why you need to work to the maximum. You need to amplify the input signal to the maximum operating voltage, so that when you work in a range of when you work in a range of wait a second, I got it wrong. When your information is basically in 5 volt, okay, it can be anything. When you go to ADC without changing the level, let's say for example here the ADC is 10 volt, okay, you will basically have your information only swing at this point. All right. Whereas you need to know that the ADC basically converts from 0, 0, 0, 0, 4 bits to the maximum of 10 volt at 1111. If you are getting just at 5 volt, what is your information here, guys? Can anyone help me? Just half of this thing. Berapa? Betul ke? I'm not sure. All right. So if your information is not being amplified, basically your full scale information is basically just down here. Okay. That's why just now, if the operating voltage basically change, all right, you need to amplify the signal to the operating voltage of the next unit who is going to receive your signal. In this case, you go to the ADC with gain equal to 2, so you will be amplifying your signal at this range. And of course, when you go to ADC, you will be working on the 10 volts information. So you are using a good kind of bandwidth for your signal, all right? And then from here, okay, from here you are looking at mana tadi? You are looking at 0.05 precision. Okay, so how to find the number of bits just now? 0.05 divide by berapa volt? 5 volt. So berapa N guys? Berapa number of bits minimum to get 5 millivolt precision out of 5 volt. Okay. Forget about this 10 volt. We go back to we go back to we go back to 5 volt. Okay. So what kind of N do I need so that my precision is basically maintained? Berapa guys?
10.
10 bits. Betul ke? My formula can be wrong here guys. Guna formula yang tadi just now in the example. Okay. Berapa bit guys? Do you calculate by N? Tadi punya formula apa? So I have my precision maintained at 0.05 volt. Okay. Bagi dengan apa? The full scale voltage. Sorry. 1 over 2 to the power of N darab 5 volt to get 0.05. So this is the formula. Okay. Berapa N? Boleh kirakan tak?
7.
Exact value berapa? Mesti ada
6.64.
6.64. Okay.
Yes.
Betul. So of course we take kita ambil higher. So N minimum is 7 bits. So my ADC must take minimum 7 bits so that my precision is maintained and I can get at least 0.1 punya accuracy goes here. Okay. So from there, you can. This is basically how the system should be designed. Okay. To make sure that the sensor that you are working with the right transfer function that you selected, and from there, how do you design the system of instrumentation, which includes the signal conditioner and ADC, to make sure that you don't miss the information. All right. So in this case, you need at least 7 bits so that you maintain the precision. Any question, guys? No. No question. Semua dapat yang faham kan? This is a very basic one lah. Okay. I'm going to see the analog multiplexer. Okay. We'll look for some data sheet. Okay, I just want to show you this one, 16 channel. This is 8 channel. Yang mana bagus sikit? 4 channel. Let's just go to this one. This is analog multiplexer. All right. I hope you can see this thing. All right. So if you can see from there, yeah, this is single supply. Okay, you can basically see from there. This is, look at the switching time here. Okay, so I think this is the most important criteria. Fast switching time, 20 nanosecond on and 30 nanosecond off, meaning that 20 nanosecond on, this is the fastest, and 30 nanosecond off. All right. So in this case, you have this kind of pass for this what they call that multiplexer. So you say just now they have 20 nanosecond on, 20 nanosecond on, 30 nanosecond off. This is 20. This is 30 nanosecond. So the total switching time from one sample to the next sample is 20 plus 13 nanosecond. So you are talking about 33 nanosecond, which goes to 1/33 nanosecond. Berapa frequency? Can somebody calculate for me? We are trying to get the switching frequency. Tolong kira, guys.
0.03.
0.03 what? 1/33 nanosecond. Sorry. Nanosecond, guys. Betul kan? So berapa hertz kat sini? I must get something in hertz. Some kind of megahertz or something.
30.3 megahertz.
30.3.
Yes.
All right. Meaning that using this multiplexer, you can design your own application up to 30.3 megahertz. All right. Meaning that these chips can do switching fast enough. Okay. Sorry. There must be say something on the noise. Leakage current. Okay. So this is the basic information which you can basically get. All right. Dynamic characteristics. I am looking analog switch resistant. Leakage current also information which you need to be careful, because again during the switching time, some information from the different channel can be leaked to the other channel. In this case, we are having information in terms of leakage current, source current, drain current, everything. They have some value in nanoamps here, so you must expect some information loss in this particular case. So this is time information in the dynamic characteristic. This is time switch on. This is also time what they call that, switch off, and then they have break before delay and all that. All right, and this one, channel to channel crosstalk. So you must also be careful about this when you select a multiplexer. Okay. So just now we were looking for the crosstalk. If you have again for multiplexer, if you have multiple channel, okay. Sometime when the switch actually happens to connect to this one, okay, because this is IC chips. In IC design, there are leakage current, so you must expect the information from this line actually leak to the adjacent line, okay, depending on the information given in the datasheet. In this case, you are having something on nanoamps. All right, from here, for example, if your current is 4 milliamps, right, you must expect that the the current is leaked by a few nanoamps to the adjacent channel. That's why when you choose multiplexer, you have to choose the lowest or the minimum leakage current, so that your information is basically preserved. All right. So this is something about analog marks. Let's go and have a look on digital marks. I'm looking for datasheet. Any kind of digital multiplexer, 4-channel analog multiplexer. Let's randomly take this one and see what they have to offer basically. Alright, now we are looking at SEMM3252, 4-channel analog multiplexer. Sorry, this is analog multiplexer, not digital. I'm looking for digital one. Let's go back. Analog multiplexer, digital multiplexer. Let's come down here. This is digital multiplexer. So you are looking at data input. All right. So because you are looking at a digital one, you should expect the information from what they call that, the input information is in the form of digital 0101. Okay. Also in the same kind of chips, you should expect the same thing here, 20 nanoseconds or 26. So this is fast enough. All right, up to megahertz speed. So basically you know what kind of sampling frequency that you need, so that you can select the what they call that, the right switching speed for the multiplexer. Okay. Of course, multiplexer, you have to always select the channel. Select the selection of the channel is basically using this CBA input. All right. For example, if you put at what they call that, this ABC. If you put what they call that, low at these 3 points, here you are basically selecting D0. All right, D0 should be pin number 4 here, D0. Okay, basically if you put ABC as low and low, you are selecting the switch to go to the D0, and the logic from D0 will be passed to Y at this particular time. So logic 1 will basically be passed to the output of the chips, and then if you change the selection logic again of the ABC, you will basically select channel number D1. Okay, channel D1, and then whatever logic at channel D1 will be passed through at this Y output. All right, so this is basically the operation of multiplexer. In this case, digital. All right. Again, the switching speed basically depends on the information given. In this particular case, we have here 26 nanosecond switching time. All right, it's fast enough. Okay. Of course, they will always give the what they call that, operating voltage. All right, so that you can always include this in your calculation. Okay. And DC input, in this particular case, this multiplexer only accept maximum, from the range. This is input voltage from negative 1.5 to positive to VCC plus 1.5. So in this case, your VCC is your power supply is at 7 volts here. Okay, if your power supply is at 7 volts here, so the input voltage that can go in is basically from negative 1.5 to 0 to 7 volts here in this case. All right. So because this is digital, so it just goes to 0 or 1 logic at the end of the day. All right. Input rush time, fall time. Okay. You have a lot of information here for you to consider when you want to use this IC chip for the design. All right. This is the rush time and everything to just make sure you get the right signal in. Because when you work for digital multiplexer, your input is in this form. Okay, so this is 0 volt. This is VCC. Just now, which goes back to your power supply, and these IC chips, they say that V input high, V input low. The time is they have given you the rise time and the so that you can give in the right information of the input. All right, because you have to know that from here to this point they have some kind of delay. Okay, in terms of second, which you have to basically make sure this thing is right so that the multiplexer can have sufficient time to read your logic level, either 0 or 1, right? So that is basically how you should work with the multiplexer. Now I'm looking at, let's say, 16-bit ADC. Okay, I always forget data sheet. Okay, so we can high-speed ADC, 16-bit, 16 channel, all right, 16 channel, 16-bit, all right. So pay attention to this, guys. Of course, just now we are looking at input signal going to a max, then they go to ADC. Okay, this is a very basic block set that you can always split things up into this kind of architecture. But this is very basic and very old. Nowadays they have basically the max going into one ADC, so that you can, this ADC can do the works of multiplexer and also can do their own work in changing the logic. All right, so in this case we are looking at 16-bit ADC, 16 channel. Okay, of course, because we have 16 channel, you must always look at the conversion time, and they say here data sampling rate is 125 kilosample per second, meaning that in 1 second you can have 125,000 sample of 16-bit data. Okay, so this is the maximum. If you are using something at lower rate, it should be no problem. Okay, ADC. Okay, you can practically see this thing. They have some kind of marks here. Okay, you can have analog input here, and then 16-bit ADC conversion. Okay, and that's the most important thing that you need to see. Okay, the rest are all tak ada apa lah kot rasa. So everything always goes back to the supply voltage, alright. If you want to do conversion, you have to go back to the supply voltage, because everything will be conversion calculation will be based on the supply voltage. This is logic level, nothing much. Yeah, there's the chip, the pin map. You can see where the input is, analog input and all that. For the ADC, the rest are all tak ada apa lah. So this is serial interface timing. That's alright. You will have to study this thing when you really want to design later on. Okay. So that's more or less what I want to cover today. If you have any question, you can ask now. Guys. So basically today we basically look at a little bit on the ADC things, and we have seen some we have basically seen some how we solve some small problems of designing system of instrumentation from the sensor stage. All right, if you were to be given that kind of same thing, you basically know what to do, you know. Yeah, I think, and we also look at a few data sheets of important elements of instrumentation system just now. All right. Of course, this lecture is recorded. The previous lecture also recorded. I forget to share with you. I will get this thing shared by today, inshallah, for both lectures. All right.
Thank you, Doctor.
Yes. Do we have questions, or we want to wrap up and close?
I think it's okay, Doctor. Just hope they
Alright.
did.
All right. So I assume no question then. All right.
Yes.
Okay. So if there is no question, I have to ask you about test 2, guys. Where do you want it, guys? When do you want it? Sorry. Can we do it? Can we do something like this weekend? Just test two question, 1 hour test. I'll basically give you the what they call that, the question in PDF, in WhatsApp. You can basically what they call that, view the question from WhatsApp, and you can answer on your own paper, and you can upload to me either through email or in e-learning. Maybe e-learning. Okay, that's how basically it works. And it will basically, Sunday you have class. What about Saturday? This Saturday, yes. Boleh, eh?
It's okay, Doctor.
Okay, I think we can work this thing out on Saturday. I will be covering mostly on this lecture and the previous lecture. Okay, on microprocessor things, on the what they call that, yeah, most of the question will be covering this lecture and previous lecture, of course, with some basics on the fundamental of instrumentation, in which we have done the revision. All right.
Okay.
But with special focus on this ADC, the special focus on this data conversion microprocessor thing. All right. It's more on designing system of instrumentation. I will pass. Sunday morning we have the active control system final exam. All right. Okay, guys. It's okay. You can basically discuss on the WhatsApp group. Okay. Once we find one good time, then we just go for it. We'll just do the test from there. Okay. In the meantime, I will of course, prepare your assignment lah kot. You all dah buat group ke? Have you guys get into the groups for the assignment? Done, right?
No.
No?
Yes.
Okay. You have total 22 students. If we have 3 students in one group, we have more like 7 groups. All right. So just find group member of 3. Okay, I will prepare something for you to do. All right. Simple one. It won't take much time. Okay.
Okay.
I will give you some kind of question which you need to solve, and just send it in the e-learning. That's all. One simple problem for you to work. All right. It should be fast enough.
Excuse me,
Okay.
Doctor. Can
Okay,
we
guys.
have the
Thank you very
exam
much.
after Sunday?
Macam mana? Again?
Doctor, can we have the exam after the test too after Sunday?
Sure.
Maybe.
We can always do that. Just put on some notes on the WhatsApp group so that everybody can say something. If everybody agree, then we can just proceed. All right.
Oh, okay, Doctor. Okay,
All
thank you.
right. Thank you very much, guys. I think that's all for
Thank you,
today.
David.
Yes, I'll see you again
Okay.
in the next engagement. Thank you very much, guys. Assalamualaikum.
Okay.
Had a very good evening.
Masalam.
Thank you very much, Doctor. Thank you.
Thank you, guys.
Thank you, Doctor. Thank you.
Salam.
Thank you.
Waalaikumsalam.
Thank you,
Thank you.
Data.
Waalaikumsalam.